Okay, so before looking at what expectation maximization is, we are first going to do a little bit of basic study of expectation. Now we did this way back, when we were starting to look at probability and statistics part of this course, and we looked at notion of expectation. Right? And what we will see is that expectation is very important or key for the understanding of EM. So let's start with expectation. So what is expectation of a random variable, right? The expectation is defined for any random variable or a function of a random variable. So expectation of a function f of x, where x is a random variable whose probability distribution is specified by p of x, is given by a standard formula, which is that expectation of f of x is equal to the summation of f of x multiplied by the probability of p of x given the PDF over all possible values of x. Now if x is a discrete random variable, right, then the expectation has a summation there because you will sum up over all possible values that the random variable x can take. However, if x is continuous, then you will integrate over all possible values. So the expression will have an integral fx px dx over all possible values of x. Let's do some simple expectations. So let's assume that x or f of x is a constant, right? So it does not depend on x at all. So then the expected value of that function is going to be let's assume that x is discrete, so summation over x over all possible values, and since c is constant, it comes out, and the summation of p of x over all x is just going to be 1. So expected value of c will just be c. Let's take another example in which f is a function of two random variables x and y. In that case, we can compute the marginal expectation of this function with respect to either x or y, which will be written as expected value of fxy under p of x, which would just be given as fxy p of x summation over all possible values of x. So now let's get back to our mixture model, because the problem that we are trying to solve is how do we estimate the parameters of our mixture model that are all encapsulated in this theta variable, right? So theta contains all of my pi's, right, for each mixture component. So if I have only two components, then I just have one pi value, right? But if I have k components, k mixtures, then I have a pi corresponding to each one of them, which gives me the p of zk essentially. And then for every mixture specific density, probability density, which is pk of xi given theta, right, I need the parameters for that. So in this, today we are going to discuss this from the perspective of Gaussian mixture models. We'll assume each mixture component is a Gaussian, so there will be a mean and a covariance matrix associated with that. So we need to find all of those values. So one thing we discussed last time was that, even if we have this mathematical formulation of log likelihood, which in principle we can optimize on to get our optimal value of theta or the parameters, because there is a summation inside a log, the optimization becomes a little tricky. So as mathematicians, we are not very good at solving optimization problems where you have summation within a log. If it were a product, we could have done that. That log of a product would have opened up as a summation, and then you could have easily taken the gradient, right? But with this, it becomes a little more challenging. But that is not the only reason, right? You can compute the derivative or the gradient of this function, right? Or you can also employ other non-derivative based optimization methods. We saw a few examples last time, and some of them actually did pretty good for a simple data set, right? But what I'll show you today is that it's not just that it becomes a mathematically complex formulation, it also becomes harder to optimize because it has multiple local optima. Right? which is sort of the bane of any optimization problem, right? So let's look at that with a simple example on our notebook. So let's look at our notebook here, where I had shown you last time how we were working with a one-dimensional data set. It has only one dimension, but it had two modes, and we wanted to take that data and we wanted to infer the parameters, right? So I have already implemented how to compute the log likelihood of the data given some parameters, right, which basically takes in these 5 parameters. So we have 5 parameters here. We have pi, and we have mu1 and sigma1, which are the mean and variance for the first mixture component, and mu2 and sigma2, which are the parameters for the second mixture component. So we need to find out all these 5 parameters. So basically what I would have liked to show you was how this likelihood function, right, looks as this function of these 5 parameters to see these different local optima there. But clearly we cannot see more than 2 dimensions at a time, right? So what I'm going to do today is I'm going to first generate some data and using some known values for these parameters. So I'm going to assume pi is 0.5, mu1 is -10, sigma1 is 5, mu2 is 10, and sigma2 is 5. So when I sample data from this generative distribution, where all I do is that I first get a z, which is hidden variable, from this pi distribution, and then using if z is 1, then I choose the first component, z is 2, I choose the second component, and then I generate my samples. Now what I'm going to do is instead of trying to plot this function as a function of 5 unknowns, I'm going to assume that 3 of these are known. So I'm going to assume that I know what my pi is, what my sigma1 is. I'm going to set sigma1 to be the same as what sigma1 I used to generate the data, and same with sigma2. And of course pi is going to be set to 0.5, and I'm going to vary the other 2 remaining, the mu1 and mu2, and I'm going to explore a whole range of values for mu1 and mu2, right? So I use different values for mu1 and mu2, and then I compute the log likelihood using my likelihood function, and then I plot it as a function of mu1 and mu2. And what you see here, so the z-axis is the log likelihood, the x and y are the values for mu1 and mu2. You clearly see 2 peaks here, right? One corresponding to when your mu1 and mu2 were -10 and 10, and another in which mu1 and mu2 were 10 and -10. So even in this very simple example, we can see that if you now try to run an optimization procedure, it would get stuck in one of these peaks, right? Now in here, because both of these mixture components are very symmetric, the heights are exactly the same. So the global actually is same as the local optima here, but in practice that might not be the case. So when you have many components, right, and you're looking at this log likelihood function as a function of all of your unknown parameters, you will see many such peaks, and this comes because of the fact that we have this unusual form of our log likelihood function. So now we will see how can we use expectation maximization to solve this problem instead of doing a direct minimization. So let's first look at a simpler two-step approach. So one thing we can do is something that we did in Kmeans as well, is we can start with some initial estimates for theta, some initial guess, and then calculate what is the most likely value for our hidden variable given theta, right? So if I know what my theta is, I can always compute what is the probability of z of I to be 1 or 2, right, using these initial estimates. So let us work it out. So if I know, right, theta, which means I know what is my pi, I know what is my mu1, mu2, sigma1 and sigma2, right? How can I compute what is zi? What is the most likely value of zi? So we can compute it simply because we know what is p of xi, right? Given p of zi given xi and theta. How can we write that? We can write that simply by using Bayes' rule. So the probability of zi to be one of the components, let's say 1, given them xi and the theta is going to be simply probability of xi given zi equal to 1 and theta, right? And divided by the probability of xi, and of course we also need to multiply to the probability of zi to be 1, that's a prior, right? And on the denominator we have the same quantity plus probability of xi given zi equal to 0 comma theta and probability of zi to be 0, right? So this is straightforward, and we know how to compute each one of these quantities. So this quantity is simply pi, right? This quantity is the PDF of using the Gaussian for the first component, and the other one would be the PDF of xi for the second component. So pxi zi equal to 1 comma theta is, because we are assuming a Gaussian mixture model, will be equal to the PDF of xi given a Gaussian distribution centered at mean mu1 and variance sigma 1, which you can write out because we know what is the PDF of a Gaussian, right? And in the same way, and of course this part is pi, so this gives us the numerator, the denominator, this part is the same, and the other part is also going to be very same, except that you will use mu2 and sigma 2 to compute p of xi given zi equal to 0 comma theta. So you can replace all of these values and you can compute the probability of zi to be 1 given xi comma theta, right? So this lets us now to now take these values for zi's and recompute or re-estimate my parameters, right? So what I can do is, using this zi, the probability of zi to be 1 or 2 given xi, I can assign xi to one of the two mixture components, right? And then I can partition my data into two parts. One part would be those points or those xi's for which pzi equal to 1 is greater than pzi equal to 2 given the xi, and the other partition in which pzi equal to 2 is higher, right? So once I partition these 2 points, right, because I know what is pzi equal to 1 and pzi equal to 2, I can now do an MLE on each one of these partitions and compute what is my mu1 and sigma 1 from one part and mu2 and sigma 2 from other part, and then I can also compute the pi. So pi will just be the relative size, or it would be given by the relative size of your two partitions. So what you see is this is sort of, and now I can use these estimates for my theta, right, and go back and reassign zi's and then re-estimate theta and keep doing that until I convert. So it's a very interesting iterative algorithm. So it looks very much like what we did in Kmeans, right? So in Kmeans, we started with some initial estimates for centroids, we assigned points to centroids, recomputed the centroids, and then reassigned points, and so on. But this algorithm does not explicitly maximize that log likelihood function. It kind of gives you a solution that's towards that, but it's not directly trying to maximize the log likelihood solution, right? It's more of like a heuristic. So the question is, can we come up with a better algorithm? And expectation maximization is an answer to that. So the idea is that instead of assigning one point to one mixture component by looking at Ci and whichever is larger, can we work with the probabilities, right, to sort of go and find the optimal solution, right? So the idea would be that we are given at every step we are able to compute Zi, the probability distribution over Zi equal to 1 or 2, and then we combine these probabilities to update our theta. So that is how expectation maximization works. It's a principled approach to maximize any function with latent variables. So the idea is that at any iteration t, so it's an iterative algorithm just like gradient descent. So you start with some initial estimates for your parameters. At any iteration time t, you define a new function. So we actually want to estimate the we want to find the maxima of this non-convex function, this blue line, right? But clearly it's not easy to find. So what we do is that at any time we find a new function that is a lower bound of your original function. So it's always under that, and which is convex, and we try to solve that convex optimization problem and sort of move from there. So this is how it works. So let's say you have a function of only one variable. Let's say theta has only one variable. So x-axis is theta, and this is how our function looks like. It's not a very easy function to optimize on. It has a lot of local peaks. So this is our L of theta. So what EM says is that we start at some initial estimate for theta, right? So at any point, and then at that point, let's call it theta 0. At that point, we define a new function q, which depends on that estimate of theta, which is believed to be convex, right? And we find the optimal solution for that. So since this is convex, it's easy to optimize over that, right? So we find the optimal solution, and let's say that's theta 1, and then we moved on our curve for that theta 1, and then we define another convex function q there, and then we keep doing that and keep moving forward. Right? So that is the basic idea behind EM. So this is general. This is not specific to mixture models, right? So because at every point we are solving a convex optimization problem, that means that we are moving in the right direction, right? And then another thing is that because we use the expectation, so by a concept called Jensen's inequality, something that we will not look at in this class, what this also ensures is that this function is always going to be below the actual objective function. So using these results, we can theoretically show that this function will always, at every step, will move towards the optimal solution, right? Of course, there is still no guarantee that it will reach the globally optimal solution. So even this EM can also get stuck in local optimal solutions, but you can at least sort of make progress towards the right direction, right? So the EM algorithm essentially is an iterative process, just like, so it's essentially like traversing that curve. So we start with some value of theta, and at theta we sort of move from the current estimate of theta to the next estimate such that the log likelihood of the data goes up. But the log likelihood of the data, we do not directly work with the log likelihood of the data, but the expected value of the log likelihood of the data, that is what we call Q, which is going to be convex, and then we sort of optimize over that. So the idea is that we start with some estimate for theta, right? Using that, we can compute the probability distribution for zi's, right? Then we compute the log likelihood of the joint log likelihood of our hidden and observed variables. Clearly, since we do not know what zi's are, right, we cannot compute the actual log likelihood. But what we can compute is the expected log likelihood using the probability distribution for zi that we get from the previous estimates for theta, right? So that is our Q function. That is a function that is convex, and that is the function that we will now optimize on to get a new value for our theta. So this is how EM works, right? You start with some estimates for theta, compute the expected log likelihood of your data, both hidden and observed variables for x's and z's, and then you try to maximize over it and keep doing that. So there is an E step where you compute the expectation, and the M step where you maximize it, right? So now let us look at it from one particular problem that we are interested in, which is estimating the parameters for a mixture of models, where the idea is that you first define the joint log likelihood of your hidden and observed data, compute the expectation, which will be a Q, and then use it to maximize and get new values of your parameter estimates, right? So it turns out for mixture models, the expressions that you get by solving the E step and the M step are very simple, and that's because of the form of the Gaussian mixture model, right? So in E step, what it essentially does is that it computes some things that we call the responsibility, or RIK, and I'll show you what these are. And so that's all we do in E step, and then in M step you use these RIKs, right, to re-estimate your theta. So the new values for your mean and variance and pi will depend on RIK. So what we're going to do today is actually derive how we arrived at all of these values. So how did we get to RIK? How did we get to those new values in the M step? So let's consider a slightly simpler case where k is 2. So you have only 2 mixture components, which means that you have to only estimate 5 parameters. So we have the 5 parameters that we have are mu1, sigma 1, mu2, sigma 2, and of course pi 1 and pi 2. Clearly pi 1 plus pi 2 is equal to 1. So I could have just used pi, but I'm going to use pi 1, pi 2, that then it's easier to generalize it to cases where k is larger than 2. Alright, so the first thing we're going to write is the joint log likelihood of our data as a function of theta, right? So theta is the vector that contains all of these parameters. So the joint log likelihood given our, if we knew xi, of course xi we know, we have observed it, and if we knew our zi, will be written as log of p joint probability distribution for xi comma zi given theta, right, and summation over all of your data points. So let's say you have let's say I denotes the ith data point. So this we can write it out because we know the form of our mixture component, mixture distribution. So which means that we can say that pxi comma zi is pxi given zi comma theta times p zi given theta, right? So this is the log likelihood, right? And now we are going to write out what is the expected value of this. The first thing I'm going to do now is I'm going to rewrite this inside of the log quantity in a different way. So it's going to be written as a product over all mixture components over all k, pxi zi comma theta times pzi raised to power indicator function zi equal to k. Right. So this indicator function essentially is 1 if zi is equal to k, right? And this indicator function is 0 if zi is not equal to k. So this is sort of a different way of writing the same thing. So there's no magic happening here. So please convince yourself that this is indeed true. So for example, if zi was k, then the part raised to power will become 1, right? And then this part will hold. And if zi is not equal to k, then it will be raised to power 0, which will be 1, so it won't matter. So you can convert that probability into a product of all these probabilities. This is going to be k. So what is the probability of the kth possibility, right, raised to power this? So the reason we write this out is because now you can replace this pi with a summation. You can replace this product by a summation and take the log inside. It will become summation I, summation k, this indicator function zi equal to k times the log of the probability of xi to come from k comma theta. So we have also written it as pk of xi given theta, right, times p of zi to be k inside the log. So now suddenly we see that earlier we had this summation inside a log, but now we no longer have that. So we have pulled it out. So now LC gamma theta is something that you could sort of work with, but of course we don't know what Zi is. So now what we're going to do is we are going to compute the expected value of this LC gamma theta, right, the whole thing inside it, with respect to the theta that we know. So let us just before that just break this open so we can write So pzi equal to k is nothing but pi k, right? So it will be pi k times pk xi theta, right? So that simplifies things a little bit. Now I'm going to compute the expectation of this LC theta, right, with respect to our theta, because we don't know what zi is, right, to compute that indicator function. But we know what pzi given our past estimate for theta is. So the expected value for this would just be the expectation of this entire quantity, right, which is a function of zi. So zi is our only random variable right now. Everything else is just either observed or something that we have assumed is true, right, or is a parameter. So how do we work with that? Now clearly the second part does not depend on zi at all. It's only this indicator function part that is a function of expectation, and then expectation of course goes inside summations just like that. So we can push the expectation in inside of summation, compute the expected value of this indicator function, right, which is izi equal to k, times the other part will be outside of the expectation because it's independent of our random variable right now, or it does not depend on it. So what is the expected value of this indicator functions? So now let's look at that, right? So this indicator function, remember that this is indicator function is 1. It takes two values, 1 or 0. Now when does it take a value 1? If zi is equal to k. And it takes the value 0 if zi is equal to, it does not take the value k, right, which means that expected value will of this indicator function will be nothing but 1 times the probability of zi to be k, right, given our xi, and our previous estimate for theta, right, and plus 0 times probability that zi is not equal to k xi comma theta, right. Of course this part does not matter, so this can go away, which means that the expected value of this indicator function will just be the pzi equal to k given xi comma theta, right. And we know how to compute that. So if you step back to our past discussion just a few minutes back, we actually computed the expression for that. What is probability of zi to be mixture component k given xi and theta, right, which we are going to write it out as rik. So rik is just a scalar value, right, which we have derived on page 1. So rik tells you what is the probability of the hidden variable to be k. So probability of your xi to be generated from mixture component k. That's it. And we know how to compute all of these using the previous estimates, right? So we'll need the previous pi, we'll need the previous mu. So now once we have rik, we can replace it, substitute it back in our LC theta or of our Q, right? So we can say LC of theta is equal to double summation I and all k, right? And then rik times the log of pi k times pk xi given theta. So this is what our Q is, right? So now we have actually computed the expected value of our Q, joint likelihood. So that kind of concludes our E step. So E step in mixture model estimation actually ends with just computing RIK. Now we will see how to maximize our Q, right? Current estimate of Q to get new estimates for pi k and other parameters of our mixture model. In fact, I'll go through the derivation for pi k in detail, and then I'll leave it up to you to compute the derivations for the mu 1, mu 2, sigma 1 and sigma 2. I will give you the exact solutions for that. All right. So in the M step, what we want to do is we want to find the value of theta that maximizes our Q. So the first thing we're going to do is we're going to write out Q again as we saw before, right? So if you look at our expression for Q, RIK is constant, right? It does not depend on theta. We have already computed it using your previous estimates for theta. So the only thing that are unknown are pi k's and the theta specific for each mixture component. So let's first write out what the Q looks like. So Q will be equal to summation IK, right, RIK log the same thing pi k pkx theta. So I'm going to just break it up, right? So log, it becomes log pi k on one side and rik log pkxi theta, because these both are have different parameters, right? So we can optimize over different parts separately. The other one can be thought constant, right? So theta of course contains our pi 1, pi 2 all the way to pi k in a general setting, and sigma mu 1, sigma 1, mu 2, sigma 2 all the way to mu k, sigma k. So we need to figure out what is the theta that maximizes this Q, right? So we'll do it one by one. So let's first do it for pi k. So let's assume, so we can do that by simply by doing our gradient descent trick, right? So we can pose it as an optimization problem and then solve it. But for pi k, we will see that there is one thing that we have to be careful about, which are the constraints. So we need to see how to maximize this Q first with respect to pi k, right? So Q can be written as, so we're going to ignore the second part which does not have any pi k inside, right? So all we're going to do is maximize this first quantity and say that the optimal pi k is the value of pi k that maximizes this Q with some constraint, because these pi k's are part of a parameters of a Bernoulli distribution, right? Which means that they should all sum up to 1. You cannot just do an unconstrained optimization here, because that would just give you an arbitrarily large pi k, because we are trying to find the maximum, right? So subject to these constraints, now we cannot directly apply a gradient descent based method here, but we know how to solve these kind of constraint optimization problems, especially when there is a quality constraint. So we bring in our old friend, which is a Lagrangian here. So we say we define a new objective function where we bring in a Lagrangian multiplier lambda, multiply it with our constraint, which is, I bring 1 over here and say summation pi k minus 1 equal to 0. So this becomes my new constraint, new unconstrained optimization problem, which is a problem with two unknowns. One is pi k, well, all the pi's, right, and the lambda. And so the way to solve this would be to take the partial derivative of this first with respect to each pi k, and then second with respect to lambda, and that will give you, and then set that to 0 and solve those to get the optimal values for pi k, right? So of course the partial derivative with respect to pi k will be given as the partial derivative with respect to q minus lambda, because lambda just contains pi k's added up. So for any one pi k it will just be 1. So now let's look at rik log pi k, right? So this is the part that depends on pi k. So what will be the partial derivative of that? Clearly the partial derivative will be pushed through the summation of I, right? And then we'll only look at the one quantity in that inside summation that depends on k, which will be equal to rik divided by pi k. So this is the expression that you get, which means that you can write lambda or pi k as 1 over lambda summation rik. So as I said, pi k can be written as summation of all riks over lambda, and now we compute the partial derivative with respect to lambda, right? And that will actually give us back our original constraint, because lambda only occurs there, which says that summation of pi k will be equal to 1. Now I can make use of both of these quantities, right? Because we know that pi k is this, right? So summation of this quantity will be summation of pi k equal to 1, which means that summation rik ink over lambda is equal to 1. That means lambda is equal to summation or 1 over summation of rik, right? Which means that now I can use this to compute pi k. But before that, we can look at one thing, is that all of these riks, when you sum it over all k's, right? If I flip the summations, right, it is the same and it will be equal to n. Why? Because if I flip the summation, then summation of rik over all k's will be 1, because that is the sum of all the probabilities. So if you go back to our discussion on the first page, right, when we derived what is rik or pzi equal to k given xi, right, so the denominator is basically the summation. So if I sum the whole thing, then it will give me 1. So when I do it for n data points, it will give me 1 over n, which means that this way we have computed what is a new value for pi k, which is nothing but 1 over n times summation of all riks. Now you can do the same process to estimate the new mu k and sigma k, so I'm not going to derive that. What you will see is that you will get closed form expression just because Gaussian PDF is so well behaved. And you'll see very interesting results, or very intuitive. So pi k is nothing but an average of all of your riks, which is the responsibilities, right? And then even the mu and sigma have similar values. So essentially the EM algorithm for mixture estimation is nothing but in each step you compute your riks, right, using your previous estimates for the parameters, and then you actually do not have to compute q. What you do is you get these closed form expressions. So now in the M step you just find this revised estimates for your model parameters, and then you go back into each step and then n step until you converge. So that is sort of the general algorithm, or the specific algorithm for mixture models, right? Now if you have a different mixture model in which instead of a Gaussian you have something some other probability density, then your M step will change, right? Because if the re-estimation step will be a little different, won't be the same mu k and sigma k, you might have different parameters, but the E step would still be the same because you still have your riks. So one question one could ask is, what is the relationship between K-means and EM? Because at some level they do look a little similar, and it turns out that K-means can be thought of as a very specific version of Gaussian mixture model parameter estimation. So if you treat your sigmas, right, for each class as a diagonal matrix with some sigma square variance throughout, right, and if you at each step, instead of treating these probabilities for zi to be 1 through k, you convert it into a hard rule saying I'll take the highest value as 1 and everything else as 0, and then pi k simply becomes just the number of training examples that are assigned